Hey. Hi, so good afternoon, everyone. My name is Benjamin, and I'm from the Biomedical Image Analysis Group from Imperial. And today we're going to talk about generative modeling in machine learning for medical imaging. Okay, so this talk will be broken down into two parts. Firstly, I'm going to introduce the premise of generative modeling, followed by the three most common used models in literature. And then I'm going to show you two recent works that use generative modeling for the purpose of medical imaging. So what are generative models? So generative models are a class of models in unsupervised learning where given a training data set, we want to be able to generate samples that follows the same distribution of the training set. So if we have a bunch of images here, it would have some underlying distribution, which we will call p-data. So we would like to create a model, which we'll call p-model, that are able to generate images similar to that of the training data. And hence, we want p-data to be approximately equal to p-model. So the hierarchy of generative modeling can be broken down by this taxonomy. This is adopted from Ian Goodfellow's tutorial on GANs. And specifically in this talk, we will be focusing on autoregressive and normalizing flows, variational autoencoders, and finally, generative adversarial networks. So the starting point of any generative models, we begin with a prior. It is just an underlying belief of what the distribution may be. We usually pick a Gaussian because it is easy to work with and it is parameterized by two parameters, the mean and the standard deviation. So we take a sample from this prior and we put it through a function which is often parameterized by a neural network. And this neural network should then generate the data that we want. So the neural network is really trying to fit the prior onto the distribution of the data. So starting off with GANs, generative adversarial networks. So in a GAN, you have two components, which is the generator as well as the discriminator. Now the generator takes a sample from our prior and generates an image that is similar to that of our training data set. The discriminator then takes this image, as well as images from the training data set, and tries to discriminate which ones are real and which ones are fake. So the real ones should have an output of 1, and the fake ones should have an output of 0. Now training a GAN is a two-step process. First of all, we train the discriminator by taking a mini-batch sample of images from the training data set, as well as the images that are being generated, and then we optimize it according to this loss function. The next step, we train the generator, and then we train the generator using this loss function here. So the optimization equation of a GAN is written like this, and we want to optimize it with respect to and we want to maximize it with respect to the discriminator, but also minimize it with respect to the generator. So what does this mean? Here we have log of d of x. So log of d of x represents the top branch here where it is taking real data. We want to maximize this term with respect to the discriminator, so it learns to recognize that images from our training data set are real images. The second term here, log of 1 minus g of z. This is the bottom branch here where it is taking in images from our generator. And here we would want to maximize this term as well with respect to the discriminators. So maximizing this term will make the discriminator be as low as possible, which we want the discriminator to be outputting and predicting zeros. But also we're simultaneously maximizing this term with, we're minimizing this term with respect to the generator. So the generator is trying to generate an image that the discriminator will get wrong. So all in all, this is a min-max game between the discriminator and the generator, which can make training GANs quite difficult because it is very likely to fall to a local minimum. So before I go into VAEs, we will need to know how autoencoders work. So autoencoder have two components as well. It has an encoder network and a decoder network. The encoder network is just a bunch of fully connected layers or convolutional layers. It takes in high-dimensional data, which could be an image or a vector, and it outputs a low-dimensional representation Z. So Z here is often regarded as the bottleneck, which is a low-dimensional representation of the input. The decoder network, again, which is just a bunch of fully connected layers as well as convolutional layers, takes this Z latent vector and tries to reconstruct the original image. So the original image, so the input and the output should be approximately the same, which makes the loss function of an autoencoder just the pixel-wise loss between the input and the output. There are many use cases for autoencoders, and they can be adapted for tasks such as segmentation, as well as denoising and image inpainting. So extending the idea onto VAEs, the difference here is that instead of trying to map the input to a fixed latent Z representation, we want to be able to map the input to a distribution. And since our distribution is assumed Gaussian, the encoder network therefore predicts two parameters, our mean and our standard mean and our variance. So Z here is now a sampling operation, where it takes a sample from the normal distribution in accordance to the mean and the variance predicted by the encoder. So the loss function for a variational autoencoder can be written like this, and is in two parts. The first part is just a reconstruction loss, the difference between the input image and the reconstructed image. And the second term is a KL divergence. So the KL divergence just measures how different two distributions are. And since we are trying to optimize this towards a Gaussian prior, it is measuring the difference between the predicted distribution here and the normal Gaussian. So training a VAE, we can't immediately train like this. We would need to apply the reparameterization trick, because Z here is a random sampling node which does not allow gradients to flow back. So instead what we do is we introduce a new parameter which we will call epsilon. Epsilon is just a unit Gaussian with a mean of 0 and standard deviation of 1. And then this gets multiplied by the predicted variance and added to the predicted mu. So Z here is now a deterministic function. Since we never change the sampling operation, gradients does not flow back through here. Gradients can just flow back through this path as normal. So extending the idea onto convolutional autoencoders is also very simple. We just add a conditioning vector to the input as an additional channel. Now this may be useful in cases, for example, where you want to have one model to be able to predict multiple classes. And in the case of MNIST, you can have a conditioning variable to be a specific class of digits, say 1, and then you can randomly sample Z, which will generate multiple variations of 1. So finally, onto normalizing flows. Now, normalizing flows deals with the explicit mapping of densities. So what do I mean by that? So say I have our unit Gaussian again, with a mean of 0 and a variance of 1. I can draw 1,000 random samples from this distribution. Now, if I want to map this distribution to another distribution, for example this, and I know the transformation function, I can write the transformation function like this. So every point in this distribution is now mapped onto this distribution. And since the mapping function since I know the mapping function, I can also write its inverse. And the inverse will just take a point here and map it back to this unit Gaussian distribution. So in normalizing flows, it is very important that you define a function which is invertible. This forward and inverse function is the mapping of coordinates. It is required to be invertible because we need to map the probability density. So to map the probability density, we start by defining this equation here, which is just the sum of total probability of a distribution. And the sum of total probability between two distributions should be equal and they should also equal to 1, since the total amount of probability can't be more. So for example, here, if we have a uniform distribution, and if I want to stretch it a little bit, then I would need to have the maximum probability. So then what we do here is that we rearrange this equation a little bit to make the target distribution the subject of the equation. And if you recall from the previous slide, we have x equals f of u, and u equals the inverse f of x. So we can just substitute the equation u here into here to get this. Now, in higher dimension, the partial derivative just turns into the Jacobian matrix, and this here is our mapped probability density equation. So for machine learning, we can just take the log of both sides. So what do I mean by using it for machine learning? Well, if we have one distribution that we don't know, but we can also map it to a prior that we do know. And from this equation, we know this distribution here, which is the normal distribution. We want to estimate this distribution through a mapping, and the mapping is done by the function f, and this f is what we learn. And therefore, we can simply just optimize this loss function using MLE. So when we use MLE, it is trying to fit the unit Gaussian onto this unknown distribution of our data set by learning this function f. So now, how do we construct an f that is also invertible? Because f has to be a neural network, and f also needs to be invertible. So this is a field of research that has been spanning back since 2014. And one of the examples which I will talk about is masked autoregressive flow, which was done 2 years ago. So in masked autoregressive flow, you have your base distribution vector here at the bottom, and your transform distribution here at the top. And they adopt a pixel RNN style mapping function. Here, they define two neural networks, an alpha and mu, which parameterizes the shift and the scaling. So this element here is multiplied by alpha, the exponential of alpha plus the mu. The forward function and the inverse function is defined by xi and ui. So you can see here that the neural networks themselves are not actually being touched at all. They are used as they are. So here the equations for alpha and the equations for mu are shifted. So here the in-between is what is known as our f. And this therefore makes the forward and the inverse transform invertible. So when you're trying to map one distribution to another, what it is really doing is warping the space in between. So as we have our initial prior, which is the normal distribution, it is bending and warping the space so that it fits this distribution onto a different distribution that you're trying to learn. And this is similar with the inverse. So on to two recent works. This first one, which is a 3D fetal skull reconstruction, was done by Juan, which is also a member of Biomedia. So in this one, he's using a conditional VAE to reconstruct the skull segmentation. So the input of the network should be a segmented skull, and the conditioned images being fed in are the three orthogonal slices, the coronal, the sagittal, and the axial. The output of the VAE should be the segmented skull. So during testing, we don't need to input the skull. We just random sample our latent Z vector, and then we also feed in the three orthogonal slices, and this would then generate the skull segmentation. So a number of tests have been done here. The tests to see the different amounts of different slices to input. Some of them are it can be just one axial, one sagittal, or all three. And this was achieved around 0.9 dice. So the second work, which was submitted to MICA this year, is the conditional image generation of missing data. So this one adopts a network like the GQN, the Generative Query Network by DeepMind earlier last year. So here we feed in a few context slices. So context slices are just the information which are just information of an organ, and it is just a few images with a ground truth that represents the entire scene. So we train this scene using a conditional real MVP, and the conditional real MVP will then generate a latent representation of all the context slices. We then use a student trNN process to iteratively update the mean and the variance, which is the distribution layer, so that depending on the amount of context slices you feed in, it will be able to generate, try and generate a mental representation of 3D organ. So here we tested it with the ATME brains, and we fed in 4 context slices, so just 4 random slices from one brain sample, and then we're able to reconstruct the entire brain by densely sampling all the other places. So this is the talk for generative networks. Thank you very much.